In the vast landscape of scientific exploration, the realms of quantum mechanics and neuroscience may seem worlds apart. Quantum mechanics, the peculiar and counterintuitive physics of the very small, governs the behavior of subatomic particles. On the other hand, the brain, an intricate biological organ, drives our thoughts, emotions, and consciousness. However, at the intersection of these two seemingly distinct domains lies a thought-provoking and enigmatic field of study, the relationship between quantum mechanics and brain function. Howdy, I'm just some random nude dude sitting in my closet talking to myself. It's also where I celebrate the power of free thinking and encourage bold ideas. As a society, we're often afraid to challenge the norms and think outside the box. But here, I embrace the unconventional. So sit back, relax, and join me on this journey of exploration where we embrace our inner nude dude and push boundaries to discover new perspectives. This intriguing juncture sparks a profound inquiry into the nature of cognition, memory, and consciousness. Can quantum mechanics, a field known for its mysterious phenomena like superposition and entanglement, have any influence on the way our brains operate? The hypothesis is that the brain, with its billions of neurons and intricate neural networks, might subtly harness the principles of quantum mechanics, challenging our conventional understanding of brain function. In this exploration, we'll delve into the implications of quantum mechanics on the brain. We'll specifically focus on the concept of superposition, where particles can exist in multiple states simultaneously, and how this phenomenon might relate to neural processing. We'll also discuss the intricate connection between quantum entanglement and brain synchronization, and how Heisenberg's uncertainty principle could introduce an element of unpredictability into our decision-making processes. But it doesn't stop there. We'll also journey through alternative theories, such as the orchestrated objective reduction, or Orch-OR theory, which proposes that microtubules within neurons could be quantum computing components influencing consciousness. We'll contemplate the mysteries of non-local consciousness and how quantum coherence within neurons might optimize information processing. However, it's not all smooth sailing in this uncharted territory. We'll navigate the challenges and skepticism surrounding the application of quantum mechanics to brain function. The warm and noisy environment of the brain, the scale mismatch between quantum phenomena and neural structures, and the lack of concrete experimental evidence are just a few of the obstacles facing this field. As we embark on this journey of exploration, we'll tread the fine line between scientific curiosity and speculation, acknowledging the unknowns and the potential paradigm-shifting discoveries that lie ahead. So join me as we venture into the realm of the quantum brain, where physics meets cognition, and where the mysteries of our own consciousness are waiting to be unraveled. Welcome to a world where the boundaries between the quantum and the cerebral blur, where we take you on a journey of discovery, one that transcends the ordinary and touches the frontiers of human understanding. Quantum mechanics is a branch of physics that deals with the behavior of matter and energy on a very small scale, often at the level of subatomic particles. When we consider its implications in the context of the brain, we enter the realm of quantum cognition. Quantum cognition suggests that cognitive processes like decision-making and information processing in the brain might be influenced by quantum mechanical phenomena. Superposition, a central concept in quantum mechanics, offers intriguing possibilities for understanding brain function. In the quantum cognition hypothesis, it's proposed that neurons in the brain might exist in states of superposition. This means that a single neuron could simultaneously be in a firing and non-firing state. Such a phenomena allows for parallel processing of information. Instead of neurons following a simple binary on-off firing pattern, they can process multiple pieces of information simultaneously. This could explain the brain's exceptional ability to handle vast amounts of data and perform complex cognitive tasks. Superposition's implications extend to memory and information storage in the brain. Traditional models of memory storage involve the strengthening or weakening of synaptic connections. In contrast, the idea of superposition suggests that memories might be stored as complex patterns of neural superpositions. This could lead to a more efficient and robust memory system, enabling rapid retrieval of information. The notion of neurons existing in superposition states also provides insights into the brain's adaptability and resilience. It allows the brain to swiftly switch between different cognitive tasks, solving various problems with ease. This cognitive flexibility is essential for learning, creativity, and the ability to handle unexpected situations. The idea of neurons in superposition has even sparked interest in the field of quantum computing. Quantum computers leverage quantum mechanics to perform complex calculations more efficiently than classical computers. Exploring how our brains might employ superposition could inspire the development of brain-inspired quantum algorithms, which have the potential to revolutionize computing and problem-solving. In recent years, the concept of quantum neural networks has gained attention. These networks are inspired by quantum superposition and are proposed as a new paradigm for artificial intelligence and machine learning. They harness the principles of quantum mechanics to perform tasks like pattern recognition and optimization more efficiently. One of the key concepts in quantum mechanics is superposition, where particles can exist in multiple states simultaneously until observed. In the context of brain function, some suggest that neurons could potentially exist in a superposition of firing and not firing, allowing for more complex and parallel processing of information. Superposition, a foundational principle in quantum mechanics, is a phenomenon where particles can exist in multiple states simultaneously until observed. This concept has intriguing implications for understanding brain function. In quantum cognition, it's proposed that neurons in the brain may exploit the idea of superposition to process information in a highly parallel manner. Instead of neurons firing in a binary all-or-nothing fashion, they could exist in a superposition of firing and not firing states. This would mean that a single neuron can simultaneously process and store information in multiple states. This parallel processing could explain the brain's remarkable ability to handle complex, interconnected information and solve problems efficiently. Superposition suggests that the brain can store and manipulate information more densely. Neurons that exist in multiple states can represent a multitude of information simultaneously. This may be fundamental to our ability to encode, retrieve, and integrate vast amounts of knowledge, memories, and experiences. It challenges the traditional view of neurons as binary switches, highlighting their potential as complex, information-dense processors. The idea of superposition in brain states could also explain the brain's remarkable adaptability. Neurons could quickly shift between different superposition states, allowing us to adjust our cognitive processes to various tasks and situations. This adaptability is crucial for learning, problem-solving, and creativity. The concept of superposition in brain function has even inspired quantum computing research. Quantum computers leverage the principles of quantum mechanics to perform computations much faster than classical computers. Some scientists are exploring the possibility of developing brain-inspired quantum algorithms, where superposition is harnessed to solve complex problems more efficiently. Quantum entanglement is the phenomenon where two particles become connected in such a way that the state of one is dependent on the state of the other, no matter the distance between them. In the brain, this could be linked to the synchronization of neurons, leading to coherent brain activity and potentially influencing cognitive processes like memory and consciousness. Quantum entanglement, a fascinating phenomenon in quantum mechanics, refers to the connection of particles in such a way that the state of one particle is dependent on the state of another, regardless of the distance separating them. Here's how it might be connected to brain function. In the brain, synchronization is a fundamental aspect of neural network activity. Different regions of the brain need to communicate and coordinate their actions for various cognitive processes, including memory, problem-solving, and consciousness. Quantum entanglement could potentially play a role in this synchronization process. It might be responsible for the rapid and precise synchronization of neurons, allowing them to work in harmony, leading to coherent brain activity. Brain synchronization is often observed through the emergence of coherent brain waves, such as alpha, beta, gamma, and theta waves. These waves represent different states of consciousness and cognitive processing. Quantum entanglement could help explain how these waves emerge, as entangled particles tend to behave in a correlated manner. This might be crucial for understanding the emergence of conscious thought and awareness. One of the remarkable features of quantum entanglement is that it can connect particles across vast distances, seemingly instantaneously. In the context of brain function, this could be linked to long-distance connections between different brain regions. It might provide an explanation for how our brain can process and transmit information rapidly, even when signals need to travel considerable distances within the brain. Understanding the role of quantum entanglement in brain synchronization could have practical applications. It might inspire the development of technologies and therapies aimed at enhancing cognitive functions. If we can harness the principles of quantum entanglement to improve brain synchronization, it could lead to advancements in fields like brain-computer interfaces and treatments for neurological disorders. It's essential to note that research in this area is ongoing, and the application of quantum mechanics to the brain is still a topic of debate and exploration within the scientific community. The warm, wet, and noisy environment of the brain poses challenges for sustaining quantum effects. However, it's a captivating field that continues to inspire scientists and researchers to uncover the potential quantum nature of brain function. Heisenberg's uncertainty principle states that we cannot simultaneously know both the position and momentum of a particle with perfect accuracy. In a brain context, this might relate to the inherent uncertainty in decision-making processes. It could suggest that some level of inherent unpredictability is built into our choices due to the quantum nature of our brain processes. Heisenberg's uncertainty principle is a fundamental concept in quantum mechanics, stating that we cannot simultaneously know both the exact position and momentum of subatomic particles. This principle has intriguing implications for understanding how our brains make decisions. One of the central ideas is that Heisenberg's uncertainty principle introduces an inherent unpredictability at the quantum level. When we consider decision-making in the brain, this unpredictability might translate into choices that aren't entirely deterministic. Instead of our decisions being solely based on predefined factors, there's a quantum-level unpredictability that adds an element of randomness to our choices. The element of unpredictability, influenced by Heisenberg's principle, could be linked to the brain's remarkable cognitive flexibility. It allows us to adapt to various situations and make creative, nonlinear decisions. This cognitive flexibility is crucial for problem-solving, creativity, and adaptability, as it enables us to explore new solutions and not get stuck in rigid patterns. Some theoretical models suggest that the brain might utilize quantum-based neural networks for decision-making. In these models, the principles of quantum mechanics, including uncertainty, play a role in how neurons process information. This could provide an explanation for why our decisions sometimes seem to emerge from complex, uncertain processes. The influence of Heisenberg's uncertainty principle on decision-making has sparked debates about the nature of free will. If our decisions contain an element of inherent unpredictability due to quantum effects, it raises questions about whether our choices are truly free or whether they are influenced by quantum-level randomness. Understanding the role of Heisenberg's principles in decision-making could have practical implications. It might lead to more sophisticated decision-making models in artificial intelligence and robotics. These models could incorporate quantum-based uncertainty to make AI systems more adaptable and human-like in their choices. Apart from quantum cognition, there are alternative theories that try to explain brain function and consciousness. For example, the Orch-OR theory proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff suggests that microtubules within neurons play a crucial role in quantum processing, possibly explaining consciousness. Apart from quantum cognition, several alternative theories and implications have been proposed to explain the potential connection between quantum mechanics and the brain. Here are some of the key theories and their implications. The orchestrated objective reduction, or Orch-OR theory, proposed by Penrose and Hameroff, suggests that the brain might utilize microtubules within neurons for quantum processing. According to this theory, microtubules function as quantum computers, influencing consciousness and cognitive processes. This theory has gained attention for its novel perspective of the brain's quantum nature and its potential role in explaining consciousness. Some theories propose that the phenomenon of non-local consciousness could be linked to quantum mechanics. Non-local consciousness suggests that our awareness is not limited to our physical brain, but extends beyond it. Quantum entanglement, which allows particles to be interconnected over large distances, has been invoked as a possible mechanism for explaining non-local consciousness, suggesting that our consciousness might be connected to a larger non-local network. Another theory suggests that quantum coherence, which refers to the synchronization of quantum states, could occur within neurons. If neurons exhibit quantum coherence, it might provide a basis for understanding how the brain processes information with high efficiency and minimal energy consumption. This could have implications for developing energy-efficient computing technologies inspired by the brain. Quantum biology is an emerging field that explores the role of quantum phenomena in biological processes, including those in the brain. Researchers in this field investigate how quantum effects might influence processes such as photosynthesis, enzyme reactions, and sensory perception. The application of quantum principles to biology is a fascinating area of study, and it has the potential to uncover quantum effects in the brain. While these theories and implications offer exciting possibilities, it's important to acknowledge that the application of quantum mechanics to the brain is still met with skepticism in the scientific community. The warm and noisy environment of the brain presents challenges for sustaining quantum effects, and the scale at which quantum phenomena operate is much smaller than the scale of neurons and synapses. As a result, these theories remain a topic for debate and ongoing research. It's important to note that the application of quantum mechanics to the brain is still a topic of debate among scientists. Many argue that the warm, wet, noisy environment of the brain may not be conducive to quantum effects. Additionally, the scale at which quantum effects operate is much smaller than the scale of neurons and synapses. While the idea of connecting quantum mechanics to the brain function is intriguing, there are significant challenges and skepticism surrounding this field of study. One of the primary challenges is the brain's warm, wet, and noisy environment. Quantum phenomena typically operate at extremely low temperatures in highly controlled laboratory conditions. The brain's environment is quite the opposite, which makes it challenging to sustain quantum effects. Maintaining the delicate quantum states required for complex brain processes amid the brain's chaotic backdrop remains a significant hurdle. The scale at which quantum effects occur is much smaller than the scale of neurons and synapses. Neurons and synapses are relatively large structures in comparison to the subatomic particles involved in quantum processes. This scale mismatch raises questions about whether quantum effects can have a significant impact on brain function. Another point of skepticism is the scarcity of concrete experimental evidence linking quantum mechanics to brain function. While there are intriguing theoretical models and observations, the direct demonstration of quantum processes influencing higher-order cognitive functions like decision-making or consciousness remains elusive. Quantum mechanics itself is a highly complex and counterintuitive field of physics, and its application to the brain introduces additional interpretational challenges. The relationship between quantum phenomena and macroscopic brain processes is not well understood, and there are multiple interpretations and hypotheses regarding how these connections might work. The application of quantum mechanics to the brain often intersects with discussions about the nature of consciousness. This is a deeply philosophical and complex topic, and the connection between consciousness and quantum mechanics remains a matter of debate among both scientists and philosophers. The potential implications of quantum brain theories raise ethical and philosophical questions. If quantum mechanics plays a role in consciousness and decision-making, it could challenge our understanding of free will and moral responsibility, leading to profound philosophical and ethical considerations. Our journey into the intriguing intersection of quantum mechanics and brain function has been a voyage through the captivating landscape of ideas, implications, and challenges. As we conclude this exploration, several key takeaways come to light. First and foremost, the notion that the brain might exploit the principles of quantum mechanics introduces a paradigm shift in our understanding of cognition. The concept of superposition, where neurons can exist in multiple states simultaneously, challenges the conventional binary model of neural processing. It invites us to consider a brain that operates with unprecedented parallelism, enabling it to handle vast amounts of data and tackle complex cognitive tasks with agility. The connection between quantum entanglement and brain synchronization reveals the potential underpinnings of our conscious experience. The idea that interconnected particles influence the coordinated activity of neurons sparks further questions about how our brains create a coherent sense of self and understanding of the world. Heisenberg's uncertainty principle adds an element of unpredictability to our decision-making processes, challenging the notion of free will and introducing quantum-level randomness into the equation. This raises profound questions about the nature of our choices and their relationship with quantum mechanics. We've also touched on alternative theories, such as the Orch-OR theory and non-local consciousness, which open up new avenues of thought and research in understanding quantum brain. These theories not only provide fresh perspectives, but also bridge the gap between physics and neuroscience in unexpected ways. Nevertheless, we've confronted the challenges and skepticism that face this field. The warm, noisy, and complex environment of the brain presents hurdles for sustaining quantum effects. The scale mismatch between quantum phenomena and neurons raises questions about the practicality of quantum processes in the brain. The lack of concrete experimental evidence and the interpretational challenges within quantum mechanics add layers of uncertainty to our journey. The quantum brain remains a mysterious and captivating frontier where the boundaries between the physical and the mental blur. While the journey has raised more questions than answers, it's a testament to the human quest for understanding. It highlights the dynamic interplay between scientific curiosity and skepticism, where we continue to push the envelope of knowledge. As we step away from this exploration, one thing remains clear. The quantum mechanics and brain function relationship is a topic that thrives on curiosity, debate, and a deep appreciation for the complexity of our brains and the universe they seek to comprehend. It's a testament to the remarkable interplay between two seemingly distinct worlds, reminding us that the boundaries of knowledge are ever expanding. The intersection of quantum mechanics and brain function is an intriguing area of research. It opens up exciting possibilities for understanding consciousness, decision-making, and cognitive processes on a deeper level. While there's no consensus in the scientific community, exploring these ideas push the boundaries of our understanding of the brain and the universe. Thanks for tuning in. I hope you found this video informative and thought-provoking. This is the point where others tell you, if you enjoyed it, give it a thumbs up and consider subscribing for more content just like this weird stuff. But we know that kind of thing is for losers. Don't be a loser. And as always, I welcome your feedback and ideas for future videos in the comments section below. Until next time, keep exploring, keep learning, and keep embracing your inner nude, dude.